Chapter 8, Estimating with Confidence. The first section is confidence intervals, the basics. So we talked a little bit about in class today using the example with estimating height, but we are going to be talking about what really is a confidence interval. How do we construct a confidence interval? What does it tell us about a certain value, a certain parameter? And here we go, the basics. So this was an activity we did in class briefly. So the idea was that we would take a sample of 16 observations from a normal distribution, from a normal population, where we did not know what the value of the mean was, but we were given the standard deviation value. Then this value right here, 240.79, that is a sample statistic, right? That's a sample mean. And then from there we we briefly discussed how do we try to determine what the actual value of M was. So this is where confidence intervals would be useful. So definitely go ahead and write down the definition of point estimate. So point estimate is a single estimate of a population parameter. In this example, that will be the 240.79. The sample mean would be the point estimate. And a point estimator would be which statistic are you using, right? So the statistic in our case would be the sample mean, and the point estimate would have a value of 240.79. So slight differences when you're using the two terminologies, really describing the same things. Estimator is what is the actual, what is the statistic? So it might be a sample proportion, it might be a sample mean, right? Like in this case. Point estimate is the value itself. Oh, anything in the previous one? Okay. So here's a couple examples, and just try these on your own. So you're trying to figure out what's the point estimator in each of these examples and what's the point estimate. So I would just pause real quick, try A, B, and C, and identify what the point estimate and the point estimators are. So pause now. So A, you have a sample of 10 golf balls, and you're trying to figure out how far each one's being hit, right? Here are the distances. So what you can do here is you can find the median of the sample of 10, and the median would actually be 285 yards, and you can use that as your point estimator. So the point estimator would be the sample median, while the point estimate would be 285 yards. Then in B, you're trying to investigate the variability of the distance traveled by the golf balls by estimating the interquartile range. So here, the point estimator would be the sample IQR, while the point estimate would be the actual value, which if you calculate it would be, I believe Q3 is 287, Q1 is 284, once you put them in order. So the point estimate will be 3 yards. And the last bit, the math department wants to know what proportion of its students on a graphing calculator. They take a random sample, find that 28 out of 100 students have a graphing calculator. So the point estimator is sample proportion, while the point estimate is the actual value, 0.28. So, like in the previous example, in the how we opened this video, we had this mystery mean activity where we calculated a sample mean of 240.79, right? Which is definitely not what M is. Most likely not, right? The odds of that happening are very, very, very low. But given that this is a point estimator, this sample mean, it wouldn't be that far off to say, hey, you know what? M, or mu, is probably really close to this sample mean. So how do we even start to talk about how close the point estimator is to the actual value of m? So then, having one sample mean or having one point estimator usually is not going to be enough data. So we're going to want to do this many times. So continue to take samples of size 16 from the population with the mystery mean and a standard deviation of 20. There's what the distribution might look like. So continue to take them, and you're going to end up with these different sample means. And these statistics will vary, and that's okay, right? They should vary just by the very nature of what we're doing. And then we would create a sampling distribution of all the x means, or the sample means, right? Again, we still don't know what the mean is, but we do know that the distribution of sample means will be much narrower, or would be more precise than the population distribution itself, right? Due to this calculation here. I believe the old standard deviation was 20 for the population, and we're taking samples of size 16, so we're dividing 20 by 4 to get a standard deviation for the sampling distribution to be 5. So what we're going to do is use that statistic that we calculated in the beginning to be a point estimate. So 240.79 is our point estimate. Again, is mu, the mystery mean, going to be exactly the same as that value? Most likely not, but it ought to be a good estimate. So we know from the previous slide, when we create that normal distribution curve, right, we have a new standard deviation of 5. And if we throw it back to chapter 2, we know that normal distributions have certain properties. And a key one is this 68, 95, 99.7 rule. If you recall, that just means 68% of the data or observations in a normal distribution live within one standard deviation of the mean. 95% of observations live within 2 standard deviations of the mean. And 99.7% of observations in a normal distribution live within 3 standard deviations of the mean. All right. So if we want to make sure that the mystery mean is within 2 standard deviations of our distribution, we can multiply the standard deviation by 2 and say, you know what, x bar will be within 10 units of the mystery mean. And if our point estimate is within 10 points of the mystery mean, then the mystery mean must be within 10 points of the point estimate. Right? It's kind of like if I'm standing in front of you, the distance from me to you is the same as the distance from you to me. So if we use x bar, right, the point estimate 240.79 as our point estimate, then 10 units in either direction from that value should capture the mystery mean in about 95% of all samples of size 16. Right? And we get this 95% from the rule, right? Because 10 is 2 standard deviations from the mean in either direction. Excuse me. And here's our conclusion, right? So if our x bar value, if our statistic was 240.79, then we would be saying that, you know what, the interval from 230.79 to 250.79 should capture the mystery mean in about 95% of all possible samples of size 16. So takeaway here, right, the point estimate in our case was the 240.79. If we were to go in either direction a certain number of units, then we should capture the true mean in that interval. And that interval is what we call the margin of error, right? This many units in one direction and this many units in the other directions. So this is how we construct a confidence interval. This is a good, I should definitely write down the definitions here. So we will definitely get a little confused, I think, early on about how to interpret, something like a 95% confidence interval versus a confidence level of 95. They do talk about very similar things, but the way in which we interpret them are different, so we'll be very careful with the wording. But again, right now we're talking about the basics. So to come up with a confidence interval, take your point estimate, which is usually some sort of sample statistic, and then add or subtract a certain value from it, which is a margin of error. Again, we'll talk about how to construct that margin of error, but that's really what a confidence interval is. Anything from this page? Oh yes, so we've seen this image before. So we will be working with this applet, which I think is a nice visual of how these intervals work. But if you look at each one, so like this first one right here, there's an orange dot, and on either end there is a little, I don't know, what we call that, tails coming out of either end. And for each of these, you will notice that the orange dot is in the center of these, right? So each of these orange dots is a different point estimate, right? So that these are maybe your sample means that you calculate from different samples. So in the first sample, the sample mean was very close to the true value of the parameter. And then these green lines are what we call our margin of errors, right? So if you look at these between the green endpoints, notice that all of these samples, except one, right, was able to capture the true value of the parameter, while this one was not able to, right? The sample estimate was too high, unfortunately, so therefore even the tails in the margin of error was not able to capture it. But again, like we said, there's a certain percentage, right? So if we were doing plus or minus 10 for the margin of error, that means 95% of these intervals should be able to capture mu. Well, it looks like, I don't know how many there are, but it seems like 95% is quite right. I think doing this together will be helpful. So look forward to that. Here we have another example. So let's take a look at this one real quick. So there's a company and they want their employees to be in good physical condition. So they give a pedometer, which is like an old school Fitbit, right? That just counts how many steps you're taking. So they give it to 50 people, and then they collect data on how many steps they took in 24 hours. The company statistician reports a 95% confidence interval between 4,547 steps to 8,473 steps. So how would you interpret this confidence interval? Right? So because they're using a 95% confidence interval, we could claim that we are 95% confident that the interval from 4,547 to 8,473 steps captures the true mean number, in our case mu, of steps taken per day for employees at this company. And we're going to use that term or that wording a lot. We are 95% confident that, whatever that confidence percent might be. So B, what is the point estimate that we used, and what is the margin of error? Well, if you recall from those with the orange dots and the green whiskers on either side, we know that the point estimate has to be in the middle, right, of this interval. So whatever the middle is, just add these two values together, divide it by 2 to find the average, and you'll see that the point estimate is 6,510 steps, so the midpoint. And the margin of error is the distance from the endpoint of the interval, so either one, from the midpoint. So if you find the difference, the margin of error ends up being 1,963 steps. Last but not least, the company guidelines suggest that, hey, you should be taking 10,000 steps per day. So is that being met on average? Well, none of the values in the interval, right, are at that 10,000 step mark. So we could say there's pretty convincing evidence that the employees of these companies are not reaching that 10,000 step mark on average per day. So they are not reaching that mark. Okay. So I would definitely write these definitions down. So like we said before, when you are interpreting confidence intervals, right, we would start with this idea of we often use 95%. So we are 95% confident that the interval from lower end to upper end captures the actual value of the parameter, right? And we like to use this captures, and we'll talk more about that in class, why we say that. And then when we get to interpreting confidence levels, this is a nice template that we use, right? If we take many samples the same size from said population, about 95% of them, right, 95% of those samples will result in an interval that captures the actual parameter value. So what I want to point at, what did I want to point at? Oh, what I want to point out is that notice that the confidence level definition does not even mention the endpoints, right? Doesn't mention this kind of blank to blank. Because a confidence level is describing the confidence that we have in the method we're using, not necessarily the values that we end up with, right? So it's really not focused on the interval itself. For that is up here. We're really just confident in the method that we're choosing to use, right? Whatever interval it spits out is not what we're interpreting when it comes to confidence levels. And we're getting to the later bits of these definitions. So again, confidence level is more about how much trust or confidence we have in the method we're using to produce the said intervals. Again, it doesn't really matter what the values of the intervals are. And this is a key bit, right? Kind of going off what we've just been talking about. Confidence level, which I think in this case we're going to be using 95%, does not tell us the chance that a specific confidence interval captures the population parameter. Right? If you think back to the graphic with the orange dot with a sample statistic and the green tails on either end, which represented the margin of error, right? Either for any given confidence interval that gets generated, right, it either captures the true value of the mean, the true value of the parameter, or it does not. So if it captures it, good, 100% chance that it captures the parameter. But if it doesn't, well, there it is, 0% chance that it captures the parameter, right? So this 95% doesn't tell you for any one given interval whether it captures the parameter or not. It's more of a long run thing. If you take the sample many times, right, of the same size, then that 95% comes into play, right? But for any one particular interval doesn't mean there's a 95% chance that that specific interval will capture the parameter. And we use this term plausible values. Plausible doesn't necessarily mean, right, like any possible value. It means that they're likely. So an interval, a confidence interval, will give you this lower and upper bound of values. and we're saying, you know what, if the parameter happened to be in that interval somewhere, then we wouldn't be that surprised because we would have expected that anyways. So that's where this word plausible comes in, right? The interval gives a set of plausible values. In other words, if we were to see that the parameter actually fell outside of the interval, then we would be surprised because we had captured these plausible values. I think that's about it for that page. Okay, so when it actually comes to constructing said confidence intervals, right, how do we create it, and why do we keep using this 95% confidence? So, like we said in class, right, the wider you make an interval, regardless of what parameter you're trying to estimate, right, the wider the interval, of course, you're going to have a much higher chance, much more confidence in capturing that parameter. But this interval becomes very, very, very wide. In other words, not very precise. All right, so if we go back to our definition of estimate and then a margin of error on either side, right, so the estimate is whatever sample statistic you calculate. Excuse me, earlier it was this 240.79 that we started with on the very beginning of the slideshow. And we've been using 95% because that comes directly from things we know about normal distributions. Because 95% of all 95% of observations of the distribution lie within 2 standard deviations. So we've been using the standard deviation, which was 5, multiply that by 2, and then there you have it. This was how we were creating our confidence interval, right, of 95%. So if we break it down further, like we've been saying, the point estimate is whatever statistic you calculated. To calculate a margin of error, you're going to take what's called a critical value, which in our case right now is 2, and then you're going to multiply by the standard deviation of the statistic that you calculated, right, which in our case was 5. So if you want to construct confidence intervals, a 95% confidence interval, then your critical value is going to be 2 because that's 2 standard deviations within the mean, or from the mean. If you want to construct confidence intervals at a 99.7% level, then we would have to turn our critical value into 3 because 99.7% of observations live within 3 standard deviations of the mean. And if you wanted to calculate a 68% confidence interval, then we would have to lower the critical value to 1. Right? So you have these choices when you're creating confidence intervals. 95% tends to be the most common one that we use, just because it is both precise yet high confidence. So this is kind of wrapping up that previous slide. And that's how you calculate the margin of error, is by multiplying the critical value with the standard deviation, depending on what confidence level you want for your interval. So you have the choice. And that's about it. And, oh, okay, there was more, excuse me. Well, we did kind of touch on these bits already, right? So here are some things to remember. 2 key points regarding confidence intervals. First one says, our method of calculation assumes that the data comes from a simple random sample of size n from the population of interest. At least throughout this chapter, when we're being introduced to confidence intervals, these things will be assumed or will be explicitly written, right? That SRSs of the same size has been taken from the population. And this bit right here says the margin of error in a confidence interval covers only chance variation due to random sampling or random assignment. In other words, if there is any existing bias or any bias that might stem from wording of questions or anything like that, those kinds of error, those bits of error, are not taken into account through these calculations, right? In other words, if those things are, if we have a distribution where there's bias present, this kind of procedure wouldn't really help us in any one way or the other. So sorry that got a little wordy towards the end. I was hoping to keep it under 20 minutes, but there I go again. We'll talk more about this in class. We'll do the applet, we'll do some examples, and we'll really get into the nitty-gritty when we get to 8.2, when we start to estimate confidence intervals or create confidence intervals for population proportions. Okay. All right. Have a good night. We'll see you tomorrow.